Okay, right now, new chapter, oscillations. Now, when I ask you guys what is an oscillation, you guys probably know what exactly is an oscillation, but how do you put it into words? What exactly is an oscillation? So you want to put it into words, what exactly is an oscillation? Oscillation is just simply repeated back and forth motion on either side of an equilibrium position. Okay, so a simple oscillation examples that you may have done or seen in the lab thus far could be, say, for example, your pendulum bob. Okay, this one is your pendulum bob. This one, you know, is actually oscillating because you see, what you understand for a pendulum bob is that it will actually move back and forth, left and right. Okay, so your equilibrium position is this little red line right over here. So when we say that the pendulum bob is oscillating, it's actually really just moving back and forth about your equilibrium position. Okay. Now, another second example of an oscillation system is a mass on a spring system. This is your mass spring system. Okay. So what will we know is that when this mass spring oscillates, it will tend to move up and down, right? But when it moves up and down, it's actually moving on either side of an equilibrium position too. So in our case, this one is our equilibrium position. Okay, so this is what oscillation actually is in its most simplest form. It's just repeated back and forth motion on either side of an equilibrium position. Okay, so we just settle with this definition first. Now, the part where we talk about free oscillation and forced oscillation, we don't do this one first. We go and do something else. Okay, we don't do this one first. We do something else first. That one is on the later part of your notes. So the one thing that I want to talk about is on page 5. Okay, have a look at page 5 of your notes. All right. Now, oscillation just now, as I mentioned, is just simply repeated back and forth motion on either side of an equilibrium position. Now, when it comes to oscillation, there is actually a very special kind of oscillation called simple harmonic motion. Okay, so for this special kind of oscillation called simple harmonic motion, it is actually defined as some sort of periodic motion in which the acceleration of a body is directly proportional to its displacement from a fixed point, and the acceleration is always directed towards that fixed point. Okay, this is what simple harmonic motion actually is. There's two criteria to it. The first one is acceleration directly proportional to displacement. The second one is acceleration is always directed towards that fixed point. This is criteria number 1. This is criteria number 2. Okay. Now, sometimes when we say that the acceleration is always directed towards the fixed point, it can also mean another thing. It means that the acceleration and displacement are always in opposite direction. Okay. So when you look at your exam question, they ask you to define simple harmonic motion. Sometimes you will notice that the second criteria, which is this one, may be replaced with another different answer where they say acceleration and displacement are in opposite directions. Okay. Now, this one is the definition of simple harmonic motion. But why are the criteria for simple harmonic motion like this? You will understand more about it if you look at the diagram below here. Now, let's just go with an example of a mass spring system that is undergoing simple harmonic motion below. Okay, so if I have a mass spring system, if I zoom, okay, I just leave it as this. So if I have a mass spring system and then I displace it from equilibrium, this part here being my equilibrium position, if I were to displace the mass upwards or downwards and then I were to release the mass, what you will understand is that the mass will actually just start to oscillate. You move up and down, up and down, up and down about your equilibrium position right over here, right? Okay, so what you're interested to know is what happens to the acceleration of the object with displacement from the equilibrium position. Okay, that's what you want to find out right now. Now, you first consider the case when your object is at equilibrium first. Okay. Now, when the object is at equilibrium, there are really only two forces acting on the mass. There will only be the weight W of the mass as well as the spring force acting on it. Because your mass is attached to a spring, the mass is pulling down onto the spring will pull back up onto the mass, right? That's what you're seeing as the spring force right over here. This is your Fs. This is your spring force. And then your weight, you know by now, is always going to be acting downwards, all right? So here, what we just want to know is that if you just leave your object as it is now, you don't try to displace it in any way, you just leave it there for a long time, eventually it will just settle down at its equilibrium position. Okay, it will not move up, it will not move down. If you do not disturb it, eventually it will reach its equilibrium position, right? So at equilibrium, we know that it doesn't move. We know that if it doesn't move, there is no resultant force and there's no acceleration. Okay, this is what we can actually deduce when something is at equilibrium. If it's not moving at equilibrium, there's no resultant force here, there's no acceleration here. Now, what I can say about the forces here is that in this case, the weight must be equals to my spring force so that there's no resultant force, no acceleration. That's why my object did not move in the first place. Now, what I'm interested after that is what happens when you start to make it oscillate. Let's just say your mass, you displace it, you release it, and then it oscillates up and down. So as it oscillates up and down, we know that it will eventually reach some sort of top position right over here. It will eventually reach some sort of bottom position right over here. Okay, so let's just consider this first. What happens at the top? Maybe a bit bottom position is better. Let's just consider what happens at the bottom position first. Okay, if I just look at the bottom position, which is this one, what you can actually say here is this. At the bottom position, your mass has actually moved downwards, pulling the spring even more. So your extension of your spring increases. So your extension of your spring increases, that means spring force increase. You're assuming that your spring force here is directly proportional to extension following Hooke's law, okay? So if your object moves down, it pulls on the spring, your extension increases, your spring force will increase. Now, in your case now, when spring force increase, your spring force will now be more than the weight. Okay, bear in mind that just now at equilibrium, spring force was equal to your weight. But now at the bottom position, because your mass has moved downwards, it has pulled on the spring even more, extension increases. So spring force is actually more than your weight now. So you actually now have a resultant force. Okay, because one force is larger than the other. Your resultant force is actually Fs minus W, and it will be directed upwards. Okay, so that's why you see here, I wrote here, there's a net force and hence acceleration upwards. But this one is where your displacement is downwards. Okay, you have an net force and acceleration upwards when displacement is downwards. Okay, your displacement or your mass from equilibrium is downwards here, all right? So this one is what you see, all right? Now, what about the case when I'm talking about the object is at the top position? What happens to the mass right now when I'm talking about it being at the top position? Now, when your mass is at the top position, your extension will actually decrease because you see, originally your mass was here, isn't it? Then suddenly you move up a little, your extension would decrease. Okay, so when your extension decreases, you will say that your spring force is now decreasing. Now, in your case now, because your spring force decrease, weight is now more than your Fs. Bearing in mind again that at equilibrium, now spring force is equals to weight. So if your spring force drop a little, that would mean that weight is actually now more than your spring force. So you now have a net force and an acceleration, but this time is directed downwards because you see weight is more than spring force. Your net force will be downwards. Okay, so you have a net force and acceleration downwards while your displacement is upwards. Okay, so from here, these two, you can actually see a number of things. Your F net or your acceleration is always directed towards a fixed point, which is actually your equilibrium now. Okay, if you look at the bottom position, look at where your F net or your A is directed towards. It's actually directed upwards, right? And then you look at your top position. You look at your top position. Where is your F net or your acceleration directed towards? It's directed downwards, right? So you see, it's actually being directed towards some point, which is actually your equilibrium. When you're at the bottom, your acceleration is directed towards equilibrium. When you're at the top, your acceleration is again directed towards the equilibrium. This is your fixed point here. Okay. And you will also notice one thing here. While at the same time, you can say that F net and acceleration are always directed towards a fixed point here, you will also see that acceleration and displacement are always in opposite directions. Okay, you will see that they are always in opposite direction when it concerns acceleration and displacement. So what I mean by that is, again, you look at your diagram. If this one is my equilibrium, let me just draw this line here. If you look at the bottom position, my displacement is downwards, but my acceleration is upwards. And then you look at the top position, my displacement is upwards, but my acceleration is downwards. So you see, it is correct to say that displacement and acceleration are always in opposite direction here, as well as saying that acceleration is always directed towards a fixed point. Okay, so this is what the second criteria of simple harmonic motion actually means. Okay, now how about the first criteria of simple harmonic motion, which tells you that acceleration is always directly proportional to your displacement? This one you have to refer to the statement further down. Now you can see here that if you have a greater displacement of mass from equilibrium, this one actually results in a greater difference between Fs and W. Because what I can say here is that a greater change in extension results in a greater change in spring force. Okay, so this one will actually cause you to have a greater difference between your Fs and W. If you look at how your F net is defined here, your net force is actually always the difference between your weight and your spring force. Okay, so the idea here is that if your displacement is getting greater, your spring force is also going to be greater. This will in turn cause you to have a greater difference between your spring force and weight, which in turn gives you a greater resultant force and hence acceleration. So it's from here that you actually can deduce this. If x increase, F net increase, therefore A increase. Okay. Therefore, A increase, where you can then say that A is directly proportional to displacement. Okay. So this is the first criteria of simple harmonic motion. All right. Okay, so this is just trying to explain to you these two criteria of simple harmonic motion. Okay, just all right. So this is the concept of it. Now, when it comes to something that's oscillating with simple harmonic motion, we will say that the system oscillates with simple harmonic motion. It has a angular frequency of omega. Its acceleration A is related to displacement x by this equation. Okay. For a system that is oscillating with simple harmonic motion with angular frequency omega, its acceleration A is related to its displacement x by this equation. This is actually known as the defining equation of simple harmonic motion. Okay. Now, it's from here, this equation here, that you can actually deduce the first two criteria from the previous page. Remember, I told you that for simple harmonic motion, acceleration must be directly proportional to displacement, and that acceleration and displacement must be in opposite direction. You can actually deduce this from the equation, this equation here, right? Because you can see if A is equal to negative omega square x, if I tell you that omega is constant, A will be directly proportional to x. This is the first criteria. And then after that, you will notice that there's a negative sign here. So what we'll tell you here is that the negative sign means that A and X are always in opposite direction. Okay. So in describing simple harmonic motion and its related criteria, this equation actually tells you that. Okay. So this is an equation that you use a lot in your past years later on. So just remember this. Okay, now before we move any further, there's also some terminology that we need to go through. Okay, a lot of them is something that you've learned in the wave section of AS physics. So let's just go through them again. When we talk about displacement x is actually distance from equilibrium position in a specific direction. So I emphasize to you here equilibrium position, distance from equilibrium position, not any other reference point, must be from equilibrium. And then you also have something called amplitude, which is denoted by symbol x naught. It is just simply maximum displacement from equilibrium position. Okay, maximum displacement. Now, period, capital T, is the time taken for one complete oscillation. So this one, not a big issue. You know, it's T, big T is T over N, where T is time taken, N is number of oscillation. This one gives you time taken for one oscillation. Okay. Then frequency F is number of oscillations per unit time. We know it as the reciprocal of the period. So if we know that period is actually small t divided by n, we go and reciprocal it, we go and take it as 1 over this, we're going to get n over t, which is number of oscillations over time taken. This one tells us number of oscillations per second. Okay, so up to here, this one is all something that you have learned in AS physics. Now, the last one here, the last terminology here, angular frequency, this one is where it's kind of new for you. Now, you have seen this symbol before, omega. Omega is 2 pi over t equals to 2 pi f. This one, you have actually seen it before somewhere. This one, in circular motion, you saw it in the first chapter of A2. You have seen this equation before in circular motion. But in that chapter, this was defined as angular velocity. Okay. Now, in the oscillation chapter right now, you are seeing the same equation where we tell you, Okay, maybe I write it here. Yes, in a different chapter now for oscillation, you're seeing that same equation again, where we tell you it's 2 pi over t equals to 2 pi f. But the omega now doesn't refer to angular velocity. It instead refers to something else that is entirely different. We call this angular frequency. Okay, this is a definition question that will come out occasionally in your past years. So when they ask you what is angular frequency for oscillation, it is just simply frequency expressed in radians per second. Okay, so I just repeat for you. It is frequency in radians per second. Now, to make a better sense of this, you think of it this way. If I tell you the frequency of oscillation of something is 50 hertz, what you understand is that at 50 hertz, you have 50 cycles per second. Okay, this is what you understand as 50 hertz for frequency. You have 50 oscillations per second, or rather 50 cycles per second. But you also know one thing. One cycle is 2 pi radian, or it can be 360 degrees in another different unit, but what you're interested is the one in radians. We know that one cycle is 2 pi radians. Okay, so you look at this one. If we have 50 cycles per second, if I were to take 50 times 2 pi, I'm going to get the frequency in terms of radians per second, isn't it? So when I take the frequency multiply with 2 pi, this is what I will call my angular frequency. Okay, maybe I actually I don't need to do this. This one, yeah, this is what I call my angular frequency. Okay, let me just rewrite it properly for you. This is what we call as angular frequency, omega. Okay, so if you just have f itself is in 50 hertz, it tells you 50 cycles per second. But I want to have a way of expressing the frequency in another different way. So if I multiply with 2 pi, I multiply 2 pi with frequency, what I'm actually getting is the same frequency, but in terms of radians per second only. That's why here, when you're talking about angular frequency omega, it is really just frequency, but expressed in radians per second. You take the frequency, you multiply with 2 pi, you're going to get it in terms of radians per second. That's the understanding here. Okay, and because frequency is 1 over t, you sub in for f, you're going to get 2 pi over t. Okay, so this is what angular frequency actually is. All right, so just to recap a little, it's different from your circular motion omega. All right, in circular motion is angular velocity. In that chapter, angular velocity was actually rate of change of angular displacement. Okay, it's rate of change of angular displacement. All right, there are different things altogether, although the equations are the same. All right, so just be careful about that. Okay, so this one is done. All right, so I've gone through the basics of your simple harmonic motion right now. So the next lesson that I will have with you is also going to be on this same chapter on simple harmonic motion again, but we'll be talking more about how you calculate displacement, velocity, and acceleration for something that undergoes simple harmonic motion.